not quite all of it, or some of it we go a little bit more into it than you did in Algebra 2 as far as end behavior goes. But I do think you were introduced to end behavior in Algebra 2. I just don't think you did a whole lot of it. The end behavior of a polynomial is going to be determined by its degree and its leading coefficient. So yesterday we talked about the degree, or Friday we talked about the degree and the leading coefficient. Remember, that's when it's in standard form. So just because it's first doesn't mean it's the leading coefficient. It has to be in order from largest exponent down to smallest. Now, that doesn't mean you have to put it in that order all the time, but that is the information that's going to be important in order to figure out what the end behavior is. What we're going to be talking about today are also even and odd degree functions. So if a function is an even, or the function has an even or odd degree, which is different than an even or odd function. A couple units, unit 10, we'll talk about an actual even or odd function. That has to do with its symmetry. But in this section and unit, all we're concerned about is the degree even or odd, and that's going to help us determine the end behavior. So these four graphs are the four possibilities that you have as far as end behavior goes. Now, what happens in the middle, how many turns it has, that has to do with the degree, but it doesn't affect the end behavior. So if you have a degree of 2, which is even, or degree of 4, 6, 8, 100, those even degrees, their end behavior is the same. What happens in the middle, how many turns it has? Like if you think about an x squared, that's easy, a parabola. You've been graphing that forever. It has one turn. So if it has an x squared, it's going to have one turn. X to the fourth is going to have 3 turns in it, and so forth. But the end behavior solely depends on the degree and whether the leading coefficient is positive or negative. So let's take this first one. N is the degree, it's odd, and the leading coefficient is positive. And number 2, it's odd, but the leading coefficient is negative. So these are our two options for an odd degree. So the biggest degree is an odd number. If that's the case, we're going to write our end behavior using these statements. So this column right here is the left side of the function. This column over here is going to be the right side of the function. As we move to the left, x is always approaching negative infinity. Okay, left and right has to do with the x, up and down has to do with the y. So as we go to the left, x approaches negative infinity. As we go to the right, x approaches positive infinity. So that's how this table is drawn for you. So if we look at this graph right here, this would be an example of an odd degree with a positive leading coefficient. So right here, whenever the leading coefficient is positive, that far right is going to be going up. Since the degree is odd, the arrows go in opposite directions. Odd is opposite. And think about a line. If you had a line, that's x to the first, 1 is an odd number. A line, one arrow goes up, one goes down. So they go in opposite directions. So the way we would write that in behavior, it's written for you here as x approaches negative infinity. So as we go to the left, what is happening to f of x? F of x is just function notation for y. What is happening to the function, or what is happening to the y values? So as we move to the left, the y values are going down, so that's why that's negative infinity. This side, as x approaches positive infinity, so as x gets bigger and bigger and bigger, y is going up, it's also getting bigger. So as x approaches positive infinity, f of x approaches positive infinity. The next one, if all that's changed now, it's still odd, so notice the arrows are still opposite, but now the leading coefficient is negative. That means our right arrow is going down. Positive, our right arrow is going up. Negative, it's going down. So what changes over here, as x goes to the left, the function, or y, is going up. So that's where our positive infinity comes from right there. And some people like to write the little plus infinity. I do not care if you write plus infinity or just infinity. You'll see it both ways. Obviously the negative has to be there, but it does not matter to me if you put a plus in front of the infinity or leave it blank, because nothing in front of it, the assumption is it's positive. Then as we move to the right, so as x is increasing, y is going down, it's decreasing, so therefore the function is approaching negative infinity. And what this is going to be important for is later on when we get into the limits, Okay, when we have our rational expressions, the end behavior is going to determine what our limit is. So again, this will come up later on. Last year we did limits within this unit, but we kind of took that out and saved it for unit 12 this year. So if someone says, oh, you can write it using limits, you can. We're just not going to do that yet. Okay, we're only going to use this one way to write end behavior at the moment. All right, so our other option, now we need to fill the blanks in, is going to be for even degree. So if the degree is even in both of these. So think about x squared. That's a parabola. If the leading coefficient, y equals x squared, we know that goes up. You could answer that without this chart. If it was y equals negative x squared, the parabola would face down. So again, a positive leading coefficient, our right arrow goes up, but since it's even, they both go up. Leading coefficient is negative, our right arrow goes down, but since it's even, they both go down. All right, so when we fill in the blanks, as x approaches negative infinity, so as x goes to the left, what's happening to the f of x or the y? It's going up, so it's approaching infinity. On the right side of the graph, x is approaching positive infinity, and so is y, or the function, or f of x. F of x is just function notation for y, and it's just describing what's happening to the function, the y values. So notice on even degree functions, x obviously has to go left and right. That's always going to be positive and negative infinity. But the y can either both go up or both go down. So on the second one, when the degree is negative, x has to go negative to the left, and y is approaching negative infinity. As x approaches positive infinity, meaning it's going to the right, it's getting bigger, the function is also approaching negative infinity. So notice when the arrows go the same, the function approaches the same value. Negative, still the same value, it's just going down. So our only two options are both positive infinity, both negative infinity, or one of each. Just depends on the function. And the way I remember is odd, opposite. Okay, then I just have to remember positive or negative. So my right arrow, positive, is up, and negative is down. All right, so now using that, we're going to answer these questions, describing the end behavior. Now remember, it's whatever the degree of the function is. So it could be the first term, but it might not be. So this first one, we first have to look at the polynomial. Here's the largest exponent, so that's the number we're looking at. All we care about is the degree and the sign of the leading coefficient. So that's even. Even means same direction. Leading coefficient is positive, that same direction is up. So what I do on these is I draw me a little picture. So since it's even, that means both arrows are going the same direction. So there's a picture of what that looks like. Even, same direction. That positive number means both going up. So now when I answer the question, I can just look at my little graph that I drew. And again, you don't have to. That's just something I do. So as I go to the left, I'm going up. As I'm going to the right, I'm going up. So the x is left and right. The y is up and down. All right, this second one is not in standard form. So you could put it in standard form, or you could just look at that leading coefficient and degree. That's the term that we care about. Because the way it's typed for you is not in standard form. So 7 is an odd number, so odd means opposite. And that negative is going to help us. So with opposite, our options are either down to up or up to down. We've got to pick which one of those. Because of this negative, our right's going to be going down, so that's what our picture is going to look like. Now, in the middle, there's going to be all kinds of turns. It doesn't matter what happens in the middle, just what matters what happens on the end. So, when I look at that little sketch, as x approaches negative infinity, so as x goes to the left, g of x goes up, so that would be positive infinity. And then as we go to the right, as x approaches infinity, the function goes down, so that would be negative infinity. this last one is in standard form. All we care about is that right there. So again, it's odd. So that means we're going in opposite directions. So we're going to have one of those two options. Because the leading coefficient is positive, that means our right arrow is going up. So that's how what we're going to use to state our end behavior. And if you don't need to draw a sketch, you just know that is fine. I'm just drawing the sketch because for me I think it's easier. Then I don't get them mixed up. So as x approaches negative infinity, so as x goes to the left, the graph is going down, so negative infinity. As x goes to the right, y is going up, so positive infinity. So that is how you state the end behavior. So that little statement is usually given to you right there, as x approaches. Obviously x is going to go to the left and right, always. Then you just have to determine, does y, the function, go up or down at the beginning or the end. This is also reviewed from Algebra 2 with the multiplicity. Maybe that is a new vocabulary word for you. But as far as graphing polynomials, you have single, double, and triple roots. Now we have quadruple roots, fifth roots, sixth roots, seventh. That can go on forever. But I would never make you graph anything other than something with a root of 1, 2, or 3. So a single root, if you remember from Algebra 2, cuts through the x-axis. Okay, it just cuts. A double root bounces through the x-axis, and a triple root flattens through the x-axis. Maybe curves, bends. Those might have been words your Algebra 2 teacher used. But those are the only three that we would expect you to have, or expect you to be able to graph. So something that cuts might look like this. Okay? Or, I mean, it might look something like that, depending on what the degree is of the function. So something that just cuts through. And that's considered to have a multiplicity of just 1. Means it counts one time. So on our 8.1 notes, we had that one polynomial we factored, and it was x to the third, so that we said that counted 3. So let's say this is negative 3 right here. That means that factor would be x plus 3 to the first. That just means that root counts one time. It has a multiplicity of 1. That's all multiplicity means. How many times does it count? If we had a double root, it's going to bounce. So it's going to hit the x-axis and bounce back up. So let's say that's negative 3. That would still be a factor of x plus 3, but since it bounced, it would have a multiplicity of 2. So something that counts double is going to have a multiplicity of 2. Something that triple has a multiplicity of 3. And what that looks like is it comes down here and kind of flattens through the x-axis. Let's say that flattens right through at 3, so that factor would be x minus 3, and since it flattens, it would have a degree of 3. So it just means it counts that many times. So if we had a y equals x to the third, that means we have 3 zeros, but it might only cross the x-axis once, because x minus 3 times x minus 3 times x minus 3, it counts 3 times, but it's repetitive, so it just makes that shape through the x-axis. Okay? So again, all that minus maybe the word multiplicity is reviewed from Algebra 2. So now let's sketch a graph. So sketching a graph of these, in order to do that, we need it to be in factored form. Okay, we're not going to make a t-chart, plug in values, plot all those points. We're not going to draw an actual graph of it. We're going to sketch a graph and then state the end behavior. So in order to do this one, we have to go back to what we did in 8.1 and factor this one first. So f of x equals, we can take out an x to the third, and we're left with x squared minus 16. Now it's still not quite factored. We can't do anything with that yet. So one more step. X cubed, this is the difference of two squares, so x minus 4, x plus 4, or x plus 4, x minus 4. So now that it's in factored form, now I can plot this and draw a sketch of it if I didn't have a calculator. So I find my zeros. X equals 0, 4, and negative 4. And so I plot those on the graph. 0, there's negative 4, and positive 4. So we know at 4 and negative 4, it's a single root, so it's going to cut through the x-axis. At 0, it's a triple root, so it's going to do that little bend through the x-axis. So we have to figure out, do we start high, do we start low, what we're going to do as far as when we're sketching this graph. So we can look back at the original. So the degree is 5, which is odd. The leading coefficient is positive. Those are the things that we care about when we're sketching a graph. Along with, more specifically now, we have these zeros. So if it's odd, that means we're going to go in opposite directions. So opposite means either we go low to high or high to low. Because it's positive, the leading coefficient, plus 1 right here, we're going to end up going up. So that means if I'm going to graph, I like starting on the left side of the graph to graph it. So if I'm starting on the left, I'm going to start down low. So I'm going to cut at negative 4. I'm going to flatten through 0 and cut at positive 4. And so there's a sketch of that graph. Because it's a sketch, I do not care how high you go here, how low you go here. It's just a sketch. If you want to be more specific and plug in a bunch of values, have at it. But it's not necessary. And then here, state the end behavior. So this is what we just did. Okay, earlier my class got confused because these examples were side by side, and these are just on top of each other. So exact same thing. It's just instead of side by side, we just moved it on top of each other. Exact same thing we just did with end behavior. So as x approaches negative infinity, so as we go to the left, the function goes down. So f of x approaches negative infinity. And as x approaches positive infinity, the graph goes up. So positive infinity. So that's how you state the end behavior. You just look at the graph and determine that. Or you can be given the end behavior and sketch it. We could have figured that end behavior out without a sketch of the graph if you know your table. Alright, and then number 5 is already in factored form, so we don't have to worry about factoring it. We just have to find the zeros. So the zeros are negative 4, 1, and 6. Where negative 4 is a multiplicity of 2, so it's going to bounce at negative 4, it's going to bounce at 1, and it's going to cut at 6. So plot those zeros. And you can label them because there's a little coordinate plane there. Whether you label them or not, you don't have to. If it was just an x and a y axis, you would just need to label each of those places. And then for here, because it's in factored form, we have to add the degrees. So our degree on this one also ends up being 5. 2 plus 2 plus 1. When it's a monomial in factored form, you have to add. When it's in polynomial form, it's the biggest. And then this right here tells us our leading coefficient is negative. If I did x times x times or x squared times x times a negative, that leading coefficient would be negative 1. So what that means is we're going to end going down. Remember, it's going to be opposite, so it's going to look like this. The end behavior is odd is opposite. Because the leading coefficient is negative, we're going to end up going down at the end. So negative 4 is a multiplicity of 2, so it's a bounce. So I start up, I'm going to bounce, bounce, and cut. And that all has to do with the multiplicity. And the only multiplicities we'll give you are 1, 2, and 3. If it's something bigger than 1, 2, or 3, that means you got to do some factoring, like that number 4. So then our end behavior right there as x approaches negative infinity. So as x goes to the left, the function goes up. So g of x approaches infinity. As x approaches positive infinity, the function goes down. So the function g of x approaches negative infinity. Questions on that part? All right, and this last one gives you a little bit more information. And again, this is mostly as far as writing the function, this review from Algebra 2, okay, writing the function that fits the graph from the given point. You did this exact same thing in Algebra 2. I believe it was the first semester of Algebra 2, so it's been a while since you've done it. And then the directions say you may leave your answer in factored form. You can multiply all those factors out if you want, but there's really no need to do that. It's a lot of extra work and lots of little bitty multiplying and adding and subtracting that could end up giving you the wrong answer, and now you went from having a correct answer to one little adding and subtracting error and have a wrong answer. Alright, so first I'm going to answer these questions and then I'll write the function. So the first is in an even or odd degree. So we can look at it. All we do is look at our end behavior. Both arrows are going in the same direction. If they're going in the same direction, that means it's an even degree. Odd means opposite direction. Using the graph, what's the degree? So we could figure out what the least degree is. So here we have a cut, that's 1. Another cut, that's 2. And a bounce, that's 2. So we could have a degree of 4. Now, could it be bigger than 4? It could, because remember there's those imaginary answers, and we can't see imaginary answers on a coordinate, an XY coordinate plane. So it could be bigger than 4, but we know it's at least 4 due to those real zeros that we saw in the graph. And then in behavior, we can answer that. We just look at the graph. As x approaches infinity, so as x goes to the right, the function goes down. As x goes to the left, the function goes down. So both the end behaviors should be the same, because we're looking at those arrows. Those arrows both go in the same direction. All right, so now back to that original question. Write a function that fits the graph in the given point. Now, think about a parabola. Y equals ax squared plus bx plus c. The a value tells you if it points up or down. It tells you how wide or skinny the graph is. When we have this specific point right here, we have to be able to figure out the a value. Okay, we don't have to multiply all the factors. That doesn't mean multiply all the factors together. It just means we have to find the factors, plug that in, and then that'll give us our a value. So what we do is we say g of x equals, or y equals, is fine. And then we list our factors. Now, this a right here, remember, that's going to be that number that's out in front, that coefficient that's out in front. And when we solve for a should end up being negative because both arrows go down, so we know at the end a should be negative. We're not going to put negative a here, but when we solve this, we're going to get a negative a. If not, we did something wrong. So then our factors, right here, if x equals negative 3, then that factor is x plus 3. And it just cuts, so it's a degree of 1. And then we have x equals 2. Therefore, that factor is x minus 2. It just cut, so it's a degree of 1. And then we have x equals 6. So therefore, the factor is x minus 6. Since it bounced, it's a degree of 2. So now we just have one more thing left to do. Because we were given that specific point right there, we have to go one step further and figure out what this a value is right here. Given the x on the y value right there. So remember, this is just function notation for y equals. So 64 equals a times negative 2 plus 3, negative 2 minus 2, negative 2 minus 6 squared. So you're just plugging in the values. What's the a value? Because that point lies on this graph. And so now we just solve for a. So it's a very simple adding and multiplying problem. So we have a times 1 times negative 4. Negative 8 squared is positive 64. So we get 64 equals negative 256a. Divide by negative 256 on both sides. And a is equal to negative 1/4. So now you just go replace a with negative 1/4. And there is your answer. The directions say you can leave in factored form. Okay, I wouldn't ever make you multiply all that out. It's not impossible. I actually did it yesterday. So if you want to do that, a little bit of work involved, there it is, multiplied together. Okay, the directions say leave in factored form. So instead of doing all of this, not something I would do, you can, but there's so many places to make mistakes right there. If the directions say leave your answer in factored form, just leave your answer in factored form. There's no need to do any more work than that right there. And when you have something like this, we are going to tell you, you may leave your answer in factored form, or we might not even tell you, but if it doesn't say to write it in a certain way, again, my suggestion would be leave in factored form. Now, there is something on your homework that says that on the back side it says, assume all of the zeros are integral values. Okay, maybe a word you don't necessarily know, but integral, integer. So on these graphs on the back, all it's telling you is that the zeros happen at integers. There's no decimals, there's no fractions as far as finding the zero.